Okay, in this lecture we're going to look at centers of mass. Now, a center of mass is a location, it's a place where we can pretend the entire mass of an extended object is contained. Imagine you have something like a meter stick. This is easy for people to visualize. And so if I have a meter stick here, I can place some sort of support underneath this meter stick. And if I place the support under the center, the meter stick will balance. Now, obviously, that means that the forces are balanced. We have the weight of the meter stick pushing down, and we have the normal force from the support pushing up, and that enables the meter stick to rest. But there's another point to consider. Think about having a little bit of mass here, some little dm. There's going to be a force down, dm times little g, and that's going to cause this system to want to rotate that way. But if my support is in the middle of this meter stick, there's a corresponding dm on the other side with a gravity acting on it, and that's going to cause it to want to rotate in the opposite direction. Those different moments, or those different torques, are going to balance one another. So the object's not going to tend to rotate, it's going to just remain balanced. The same as if I had my support and a single mass just directly above it. And so in that sense we can pretend that all the mass of this meter stick is right there over the support. Now, this comes into play also in certain dynamic situations where things are moving. If I take my meter stick and I throw it across the air, my meter stick is going to fly through the air, but as it follows its path, it might... That's a terrible meter sticks, but you guys get the idea. This thing is flipping as it goes through the air. But if I paint a spot on the center of mass, which we now know is right in the center for this case, that center is going to follow a perfect parabolic path, even as the meter stick is rotating around it. And so any generalized motion of an extended object can be a sum of the motion of its center of mass. So the motion of the center of mass would follow a perfect parabola, because we know that's the path that projectiles take. And then the motion rotating about the center of mass. So you would have the parabolic motion and you have the rotation of the stick about its center of mass. Those are both much simpler motions to consider than the wacky loop-de-loops of the stick as it's flying through the air. Mathematically, it's a lot easier to break the motion down into those two components. And so this idea of a center of mass is going to be something that's very important for scientists and engineers to be able to understand. Also, one quick grammar note: the proper plural is centers of mass. It's the center that we're talking about. It's the location where we pretend that all the mass is concentrated. It's going to have units like meters or feet because it's a position. And if I had 10 objects, each with their own center of mass, you wouldn't say 10 center of masses, you would say 10 centers of mass. That's the proper plural. Just like attorney general. You don't say 10 attorney generals sued the government, you would say 10 attorneys general sued the government, because it's the attorney that gets the plural. Same sort of grammatical point. So let's start with a simple example. I've got two masses here. I've got a 4 kilogram mass and a 6 kilogram mass, and I want to calculate the center of mass of this system. They're separated by 1.2 meters. It should be pretty straightforward. The formula for locating the center of mass for discrete objects like this, that means individual separate objects, not one big continuous body. So the formula is this: the x center of mass is equal to the sum of mi xi over the sum of mi. And of course, that sum over mi, that's just the total mass of the system. So I've got if you look at the units, you can see I've got a mass times a distance divided by a mass. That's going to give me distance type of units, which is what we expect. Now, what is this mi xi business about? Well, let's consider our system here. I've got 6 kilograms here, I've got 4 kilograms there. You probably would not guess that would, if I had these connected by a thin rod, where could I put a support so that this would not tip over? I think you would imagine that you would not want to put your support directly in the center like you did with the meter stick, which was uniform, because this guy is heavier. It's going to tip over if I do that. So what I would have to do is scoot and find some position closer to the bigger mass. That's where I would be able to get it to balance. And so the more mass you have at a particular position, the more the center of mass gets weighted towards that position. And so this is the formula that we would use. So let's see how to do this. Let's start by putting a coordinate system on the 4 kilogram mass. And so here's the origin of my coordinate system. And so what am I going to do to calculate the center of mass? Well, I simply will apply this formula. Now my denominator is going to be the sum of all the masses. That's 4 plus 6. That's going to give me 10 kilograms. So I'm going to calculate this sum in the numerator and then divide it by 10 kilograms. Keep that in mind. But let's consider the numerator. We've got the sum, we've got the sum of mi xi. That's just going to be equal to 4 kilograms times 0 meters plus 6 kilograms times 1.2 meters. And that just equals 7.2 kilogram meters. Now, of course, we want to divide this whole thing by the sum of mi, which is 10 kilograms. So if we divide 7.2 kilogram meters by 10 kilograms, we end up with 0.72 meters. And that would be our answer for the x center of mass. That is equal to 0.72 meters. Now, what if I place the origin of my coordinate system at a different location? Say, instead of placing it on the 4 kilogram mass, I would want to place it on the 6 kilogram mass. And then I could still calculate my sum of mi xi. The 10 kilograms is still going to be the total sum that we divide by, but this would just be the 4 kilograms. Now we have to be careful here because our distance is now minus 1.2 meters. And so we would have 4 kilograms times minus 1.2 meters, and then plus 6 kilograms times 0 meters. That term would, of course, go away, and that works out to be 4.8 kilogram meters, or I'm sorry, negative 4.8 kilogram meters. And of course, if I divide that by 10 kilograms, I get, for this situation with the coordinate system on the right, xcm is equal to minus 0.48 meters. Now, here's the thing. If I consider my green coordinate system, I found out that my center of mass was at 0.72 meters, which would be something, maybe here. But if I consider my red coordinate system, I find that my center of mass is negative 0.48 meters, and that's going to be from the red, which coincidentally would be in the exact same location. The center of mass is independent of the coordinate system that you use. It doesn't matter where you put your coordinate system. It will always point to the location where the center of mass can be considered. Now, this is how you can do it with discrete point objects. You have individual masses that are located at different spots. And of course, I could apply the same formula for a y, for a z. Doesn't matter. The formula is the same for any variable. And you can find the location of the center of mass very easily in this situation simply by doing these sums. Now, what about for an extended continuous body? Well, we're going to handle that just like we handled centroids, which were centers of area or centers of volume or centers of line rather than just centers of mass. Because when you're considering the center of mass of an extended body, well, you're talking about something where mass is distributed over a line or an area or a volume. And when you have that, some sort of extended body, the center of mass of that object, the formulas, the summations just turn into integrals. And so you can see here the x center of mass, the y center of mass, the z center of mass. They're located just by simply applying those integrals. Now, what I've got here up above is this extended mass, and I'm breaking this mass into little pieces dm, and each of those dm is going to be located with some position vector to the origin, and that position vector is going to have an x, a y, and a z. And so what I'm doing is I'm going to say, okay, I'm going to find that location of that little piece of mass, and then what I'm going to do is I'm going to find another little piece of mass, and I'll do the same thing, and I'm going to add up all of those contributions, and because I have infinitely many of them and they're all infinitesimally small, the summation becomes an integral. And so we're simply going to apply this integral, which looks very similar to the integrals for centroids, but the application is slightly different. So let's look at these formulas for just a moment, because if I consider the x center of mass, we have that's an integral over the mass of x times dm, and this is the integral over the mass times dm. Now we know this lower denominator integral, that means add up all the little pieces of mass, and what's that going to give you? Same as before, the denominator is going to give you the total mass of the system. Now this numerator here, x dm, here we have to actually be a little bit more clever and figure out how to integrate this, because the location of the little piece of mass can depend on where it's located. So we have to figure out how to represent this dm in a way that can be integrated. And typically we do it like this. If we have rho here being the volume mass density of an object, the little mass piece is going to be the volume mass density, or the mass per unit volume, that's what rho stands for, mass over volume, times dV. That's the volume of our little piece of mass. And so if I've got an area, the dm is a sigma, which is the mass per unit area, times the area. That gives me the little piece of mass contained in a little piece of area dA. And then if I'm looking at a segment of a wire or a line, the mass is lambda dl, where lambda is, of course, the linear mass density, mass divided by the length of the line. The total mass divided by the length of the line gives me lambda, and so that's the density, mass per length, times the length dl. That gives me the amount of mass in that length of line dl. Now, of course, we did this all with centroids. We calculated centroids of volumes and areas and lines in much the same way. And so we're going to have another video that I'm going to put up with some examples in it, and you'll see how these get applied, but the basic idea should already be familiar to you. Now let's consider our mass here. We looked at the torque in the example we did earlier with the meter stick. How will we consider the torque acting on the little pieces of mass and this kind of a thing? Well, if we calculate the torque across the origin, if I start with the origin here, and I draw a position vector from the origin to my little piece of mass, so this is my position vector, you might even call that r, and r is going to have, coordinates, an x-coordinate x, a y-coordinate y, and a z-coordinate z. That's going to be our position vector to this little piece of mass. And if I calculate the force acting on the mass, that's just going to be negative g times the little piece of mass dm. And of course it's j hat direction, so it's actually the negative j hat direction. The acceleration due to gravity, 9.81 meters per second squared, times dm. That's going to be the force acting on that little piece of mass. And of course, if we do the integral, everything is constant and comes out of the integral except dm, and the integral of dm over the whole mass is just the mass. And of course, m times g is the weight. And so the force acting on this extended object, when you add up the forces acting on all the little pieces that make up the object, is just the weight of the total object. You probably would have guessed that even without looking at the math behind it. But now let's look at the torque, because what we have here, or the moment, as we say in engineering mechanics, because what we have here is the position vector r and that's crossed with the force. And remember, that's just a definition of the moment, R cross F. And of course, we could put up our little determinant, and we could say I hat, j hat, k hat, and then the R is going to be x, y, and z, and then the force is going to be 0 minus dmg, and then 0 again, because there's no x or z components of the force. It's only acting in the y direction. And so if I do that determinant, what I end up with is this guy. So this is where we ended up in the last slide. We had R cross F is equal to this when you do that determinant. And we can look at this because that's just the torque or the moment acting on that little bitty piece of mass. If we want to get the moment acting on the entire object, we're going to have to do an integral. So we would, basically integrate this whole thing to get the entire moment acting on the entire extended object. And if I look at this, I can see that I've got little g, which is a constant, and the I hat, which is a constant unit vector. They can actually pull out of the integral, and what I'm left with is just an integral of z dm. And over on this term, I'd be integrating over a term x dm. Well, those look just like the integrals for the center of mass. If we look at the formula for the center of mass, it's just the integral of x dm over the total mass m. If I bring this m over, I would get m times the center of mass is the integral of x dm. And I can just simply plug that in here, or actually this one we plugged in there. I do the same thing for the z center of mass and plug into there. And when I do that, I end up with these terms. And so what I get is that the total torque about the origin of this system is mg times z center of mass minus mg times x center of mass in the appropriate directions, I hat and k hat respectively. And again, what's mg? It's just the weight. And so that gives me the moment about the origin of this extended mass. But note, that would be the exact same thing that I would get if I considered all the mass being concentrated at the coordinates of the center of mass. And so if I have an R here, Cm, I can consider that basically the action of all this extended mass, this whole mass here, I can consider it as being concentrated at this single point at the center of mass, because the torque is the same in both cases. And so mathematically, it's an equivalent way of looking at it. So that was an interesting result. We basically just proved that you can actually consider mathematically the mass of an entire extended body as being concentrated at the location of the center of mass. Now, this slide, we're just recapping a few things. If I consider the coordinate for the x center of mass, this is the formula right here, x dm divided by the integral of dm here. The mass is going to be the integral of dm, so this is just the total mass. And typically, for a volume, that's going to be rho times dv. And of course, for an area, it would be sigma dA. For a line, it would be lambda dl. We've seen all that before. This is the general approach. Now, if I look here down below, I've got the formula for the x center of mass, and it's basically just I've plugged in rho dv for my dm, and I've got an x up above, I don't have an x below. But what you can see here is that if rho is constant, in other words, if the density is uniform, that constant value will come out of the integral and it'll cancel. You'll have a rho above and a rho below. And if that happens, you'll end up with this. So this is the formula for the center of mass for constant density. And up above is the general form. So this is the general form for finding the center of mass. But if you know that the density is constant, you can just simplify using this lower equation here. And so that's basically our overview of how to deal with centers of mass. And so we're going to look at some examples in the next video.